nanomaterials, especially zero-dimensional, one-dimensional, 2D, and 3D materials. So there's different configurations how we characterize nanomaterials based on top-down or bottom-up approach. What we'll talk is how we can think of uh, a basic few of those that have made a big contribution to nanotechnology. So the first one is what we call buckyballs. So if you think about a soccer ball, and if you would take that soccer ball and make it so small that there are only 60 carbon atoms, and that gives us a shape what you call as buckyball. So this is uh, there are various names that we give it to this structure. It's basically the smallest structure that's known to human. I This is something profound about these material. You can see it's a zero dimensional. We call it zero dimensional because it has no dimension. It is so small. It's the roundest, most symmetrical molecule known to human being. And it's interesting that the scientists were the astronomers were the one who discovered buckyballs because they were seeing signal from far off astronomical objects, which would give signals that would uh, show this kind of atomic behavior. These are carbon atoms, 60 carbon atoms combined in a way, which is what we call as a football, soccer ball. And they are third major form of pure carbon. Now, we call them fullerenes also. It's a word which was given by many years ago. So I would just type they're also called fullerenes. They are uh, also called buckyballs. It's written here C60, and there's another name Buckminster, something like that. But more commonly we call them buckyballs. 60 carbon atoms. That's what you have to remember. So we start with zero dimension, and we'll look at one-dimensional 2D things today. So that's the topic. So let me uh, clear this and move on. All right. So there are lots of uh, experimental and theoretical work that's been done on buckyballs. So these were discovered at Rice in Texas. There was a British chemist, Dr. Harry Kroto, who was studying molecules, and he came for a summer to Rice University to work with Dr. Richard Smalley and Robert Turd. And it was a summer project for them, think about it. And where they discovered, and they found it in soot, the chimney where we have the black soot. And they got Nobel Prize for this work. I met Dr. Harry Kroto. This is him. I met him a few years ago. He passed away in 2016. So now these are, again, if you think about it, carbon, basic carbon in the purest form. And we see carbon other places like diamond or graphite. But what makes them important is that there are so many different reactions that can be done with buckyballs. Because of the pattern, this is just showing uh, uh, a buckyball where yellow bonds are showing double bonds and reds are showing single bonds. So the idea is that they are highly reactive, and there are many different kinds of reactions that can be done with these things. And when you talk about reaction or reactivity, just a simple figure which is showing the possible reactions that can be achieved from C60, C70. You can add more atoms, you can subtract, you can put many of them together, what you call polymerization. And polymers are plastics. So you can substitute different groups into it, essentially very versatile. Why it's important for us? Now we are getting the part where we have good understanding of nano. Now we have to think about bio nano. How do these things help us when we know they can react, they can be made into different combinations? How would they help us in the form of devices or sensors. So now, if you were to take a buckyball and sort of make it long, right? So just instead of keeping it round, add more carbon atoms and make a kind of a cylinder out of it. If you do that, we call that structure carbon nanotube. Carbon nanotubes are one-dimensional. So these are fundamentally one-dimensional structures. Why do we call them one-dimensional? Because they have only, their structure is only in one direction, and the other direction, which is the round thing, is almost negligible. So it's infinitely long with respect to its diameter. And their diameters, they come in different shapes. So 4 nanometer, 5, 10, there's so many reports of different carbon nanotubes. The idea is that they are stronger than steel and 1/6 of the weight of steel. Again, carbon in the most fundamental form made into cylinders, and we call them carbon nanotubes. Now, carbon nanotubes, and these are some figures. This graphene, what says graphene sheet, is the next thing we'll talk about. But when we get there, we'll see that you have the cylinder of carbon, and if you just cut it somewhere and unroll it, if you spread it, then we call it graphene. So that's the 2D material we'll talk about today. But let's focus on CNTs for now. So we call CNTs, carbon nanotubes, CNTs. They come in metallic, which would be conductive, and they come in semiconducting, which would not be conductive unless there is some doping done or some processing done. And they are very good conductors of heat as well. Why is that important? Because there's possibility for us to make superconductors. There's possibility for us to make devices that don't waste any energy, because heat is the number one wastage of our devices. If you are sitting, if you are taking this lecture on your laptop, you touch your keyboard and you see it's hot, right? So that's your energy bill going down the drain in terms of heat. CNTs can take care of that because they're superconductive. And if you use them on devices, there'll be no heat loss. When you make carbon nanotubes, you can make them infinitely long. So here's just a forest, right? So many of them. Left image is showing you a zoomed out image. Right one is where they have zoomed in. And you can see what you call length. So if I draw your attention on the scale. So this is a bar shown here, and there's 100 nanometer written next to it, right? You see this on the corner? So this shows you that that so small area is supposed to be 100 nanometers. So this is just a fraction of that. So these are really, really, really this real nanomaterial. So this width would be 100 nanometer. So now if you put maybe translate that with a ruler, and you can see it's probably 50 nanometer or smaller than that. This thickness here is so small that I can't even put yet. So this thickness would be so small. So we can make them in various varieties and sizes as we want. Now, where do we use them? Where do you use carbon nanotubes? We use them at so many places. We have used CNTs in ceramics, in polymers, in coatings, in membranes. And this, we talked about uh, applications in micro electromechanical systems, energy systems, medical diagnostics, chemical sensors. There's a whole bunch of applications where CNTs have been used. So that's a fantastic material that has shown lots of application in biomedical. So, and you would see that we have done studies where they have seen in living things, in animals, if they, what are the toxicity effects, or what is the body response, inflammation, inhalation, immune system, cell growth. That's this a whole bunch of work that's been done in on CNTs. CNTs are used in coatings. When you talk about coatings, very specialized applications, especially in the ship hull, right, that exposed to water, or aircrafts, or weapon system that need uh, the coatings that stay good for a long time. So there's a whole bunch of application. We'll stick to biomedical and medical for this. Now, as I was saying, you take the tube, you unfurl it, you make a sheet out of it. What we get is, we call this graphene. So it's a true two-dimensional material ever discovered. Now, for this, we can say this is the thinnest material known to humankind, thinnest, and the strongest as well, because this is one atom thick carbon atoms arranged in a pure hexagonal lattice. We say lattice, so it's kind of a crystalline material because it repeats over and over. And and this is nothing but our graphite pencil, right? So we all use graphite pencil. It's black, right? But the graphite is a bunch of graphene sheets is called graphite. The the beauty is to get one layer of those carbon, and that's called graphene, right? It's hard to manufacture, and it's hard to manufacture at large scale as well. So there were two scientists who found a very high-tech way to get graphene. So high-tech was they used Scotch tape. So they put graphite on a Scotch tape, put another tape, stick it, remove it. Some layers would come off, then they would take another Scotch tape, remove it. Some more layers become thinner and thinner until they got one single layer of graphene, and that they got Nobel Prize for that. But the idea has been around for a long time. So it was it was understood that how would a single layer of carbon behave for as far as 1946. But the graphene, or the term itself, has become more common last probably 20, 30 years. Now, its physical properties are again amazing. Stronger, lighter. It's pliable, easy to deal with, and it can stretch. So it's stretchable, and it can recover its original shape. So there's something what you call shape memory materials. So you stretch it, you leave it, it's going to come back to its original shape. There are huge applications for that kind of material. And tensile strength, if you compare with 400 megapascal, that's for steel, it has 103 gigapascal, many orders more than that. And it's light, and it's lighter than paper even, right? And they say that if you could get a single sheet of graphene cover the whole football stadium, it would weigh less than 1 gram. But the question is, how do we get that amount or that quantity together, right? So there's lots of application with optical solutions as well, optical materials that it can, it's invisible. It can let 98% of light go through. Strong material, light material, and invisible. It's amazing what are the applications that are coming up for graphene. They're using now graphene for space applications as well. It's just a couple of slides on how did they make it. So they repeated the process 20 times to 100 times of Scott. And look up on this, you'll find lots of interesting material on how to make graphene with the Scotch tape. But there are chemical ways of making graphene as well, what we call chemical exfoliation. So we take a graphite block and you put it into a solvent, and then the sheets break apart, and you can get single sheets away from that material. There's much work that's been done in energy storage applications as well, where they are using, because they are very thin, they are good conductors, so they can store charge, right? So high amount of charge can be stored. So they're using them in supercapacitors and battery applications as well. So here's an example of using graphite and making a circuit on a compact disc. So essentially, they've just made LEDs with they have lit up LEDs with 2 minute charge, and those LEDs stay up for 12 hours. So they can store so much charge using graphene. But it's not easy to make. It's it, it has no bandwidth. So bandwidth is something which is for semiconductor devices. So it can never be shut off because it there's no low there's no band pass concept with it. So it would transmit everything. Everything will go through. It's very hydrophobic, which means is how do you use with water or things that need to be wet. Expensive because it's difficult to manufacture and especially large scale. And there have been issues with duplicating results with graphene as well. All right, questions. So the basic introduction to zero-dimensional, one-dimensional, two-dimensional nanomaterials. And if we look at these things, they give very exquisite properties. And some of you may have done the KPR on those as well.